Welcome to the lecture on transportation and assignment problem. In this module, we will discuss assignment problem in which the objective is to minimize the cost of allocating a number of jobs to a number of facilities such that only one job is assigned to only one facilities. We will also discuss some applications as well as solution methods of assignment problem. Let us first define how an assignment problem can be formulated mathematically. Suppose that a company has n machines M1, M2 up to Mn, and there are n jobs J1, J2 up to Jn, and we have to assign one machine to one job. This problem is similar to transportation problem, except that the availability of the machine is 1 and the requirement of job for the machine is also 1. To formulate this problem, we define the activity variables xij as xij equal to 1 if machine I is assigned to job j and xij equal to 0 otherwise. Then the mathematical model for assignment problem can be stated as shown in the slide. The cost of assignment is summation over I equal to 1 to up to n, summation over j equal to 1 to up to n, Cij, Xij, which is to be minimized in this problem. And also we have to satisfy some constraint, say sigma Xij j equal to 1 to up to n, which is equal to 1. This is called availability constraint, and this constraint is satisfied for all I. And another constraint is sigma Xij, I varies from 1 to up to n is equal to 1 for all j. This constraint is called requirement constraint, and clearly Xij should be equal to 0 or 1 for all I and j. That means one machine should be assigned to only one job, otherwise Xij will take the value 0. We now state some important result which will be required to develop some solution algorithm. First, suppose that in an assignment problem, if we add or subtract a constant to every element of a row or column of the cost matrix Cij, then an assignment plan that minimizes the total cost for the new cost matrix also minimizes the total cost for original cost matrix. This result can be proved easily. For this, we assume a new cost matrix Cij dashed, which is equal to Cij minus Ey minus Vj for all I j equal to 1 to up to n, and Ey and Vj are real numbers. Then the new objective function z dashed, which is equal to double summation Cij dashed Xij, where the summation varies over I equal to 1 to up to n and j equal to 1 to up to n, is equal to double summation Cij minus Ey minus Vj whole into Xij. Here we are just substituting Cij dashed by Cij minus Ey minus Vj. Now, if I simplify it, then we can get z dashed equal to z minus sigma Ey minus sigma Vj, since sigma Xij is equal to 1 when I varies from 1 to up to n, and also sigma Xij equal to 1 when j varies from 1 to up to n. This shows that the optimal solution of the newly formed objective function and the original one is the same as sigma ui and sigma vj are independent of xij. We now state another important theorem. If an assignment problem with cost matrix such that Cij is greater than or equal to 0 for all I and j is such that minimum value of double sigma Cij Xij star equal to 0, then Xij star provides an optimal assignment. This result can be proved easily, since Xij takes the value 0 or 1 and Cij are all greater than or equal to 0. Therefore, minimum value of the objective function double summation Cij Xij star cannot be negative. That means it should be greater than or equal to 0, but since the minimum value is equal to 0, this means that Xij star giving the optimal solution. From these two results given in the two theorems, we see that if you can introduce a good number of zeros in the cost matrix by employing the first result, that means if we can add or subtract some constant in the elements of the cost matrix, by doing so, if you can get a good number of zeros in the cost matrix, we can find a feasible assignment for which the corresponding Cij's are equal to 0, and then we can find our optimal solution. Now, we are going to solve an assignment problem. One thing we can notice that if there are n jobs and m machines, we can find the solution by analyzing all the possible arrangements from it. If there are n machines and n jobs, then the total number of arrangements is factorial n. If n is significantly large, then the method is not suitable, because we will then have heavy computation burden. So, in order to solve these difficulties which arises when n is significantly large, a very efficient method was developed by a Hungarian mathematician D. Koenig, and by his name the method is called Hungarian method. So, by applying Hungarian method, we can now see how can we solve an assignment problem. The solution algorithm for this method are as follows. First, we have to identify the minimum element in each row and subtract it from each element of that row. And there is no harm if you can subtract the minimum element from each row from all other elements, because the optimal solution will not be changed. In step 2, we can identify again the minimum element of each column and subtract it from each element of that column. Then we draw the least number of horizontal and vertical lines to cover all the zeros. Now, if the number of lines equals the order of the cost matrix, then we go to step 5. Otherwise, we will go to step 4. In step 4, we will identify the smallest element among the uncovered elements left after drawing the horizontal and vertical lines in step 3. We then subtract this element from all the uncovered elements and add the same element to the elements lying at the intersections of the horizontal and vertical lines. Then we again go to step 3, and there we will draw the least number of horizontal and vertical lines, and if the number of horizontal and vertical lines not equal to the order of the matrix, then we will come back again to step 4. Otherwise, we will proceed to step 5. In step 5, we box that 0 as an assigned cell. For every 0 that becomes assigned, we cross out all other zeros in the same column or row. If for a row or a column there are 2 or more zeros, then we choose one cell arbitrarily for assignment. This process is to be continued until every 0 is either assigned with box or cross out. Cells having a box indicate the optimal assignment. Let us now demonstrate this procedure or method for an example. Suppose that a company has 4 men available for work on 4 separate jobs. A, B, C, D are the 4 men, and the jobs are 1, 2, 3, and 4 as shown in the following assignment cost matrix. Only one man can work on any job, any one job. The cost of assigning each man to each job is given in the following table. Now, our objective is to assign men to jobs in such a way that the total cost of assignment would be minimum. Following the steps or algorithm provided in the Hungarian method, we will subtract the minimum element of each row from the respective elements of that row. Here, in the first row, the minimum element is 20. So, we will subtract 20 from all the elements of the first row. Similarly, we will subtract the minimum element from row 2, row 3 and row 4 from their respective elements, and the same procedure is applicable for the columns. So, in this slide, the first table shows the result after subtracting the lowest element from each row from the respective elements of that row and subtracting the lowest element from the respective all other elements of that row of that column. So, now in the second table, we draw the least number of horizontal and vertical lines covering all the zeros. We see that to cover all the zeros, we need only 3 lines, but since number of horizontal and vertical lines is not equal to the order of the matrix, the optimality condition is not satisfied. So, we proceed to the next step. In the next step, we choose the minimum element which is not covered by the horizontal and vertical lines, and then we subtract the minimum element from the uncovered elements, and at the same time we add that minimum element at the crossing of the horizontal and vertical lines. And in doing so, we get the result as shown in the last table of this slide. And then again we draw the minimum number of horizontal and vertical lines. Here we draw only the horizontal lines to cover all the zeros. So, minimum number of horizontal lines needed is equal to 4, which is equal to the order of the matrix. Thus, we can say that the optimality condition is satisfied. In order to get the optimal solution, we write the results or table in as shown in the right hand side of the slide, and for finding the optimal solution, we look for a row or column where a single zero is there. And if we find a single zero in a row or column, we will assign that element with a box as an optimal assignment. Here we see that row 3 contains a single zero. So, we make a box there for the optimal assignment, and any other zero lying in that column in which the zero is there, which we make a box there, we should cross it out. So, the zero lying in the row 4 below the box, we cross it out. Then we again look for a single zero in any row or any column. If we are not able to get a single zero in any row or any column, then arbitrarily we choose an assignment with a 0 and putting a box there, and following the same technique we cross all other zeros lying in the same row or in the same column in which we put the box. So, by this way we box the zeros until all the zeros are exhausted, whether they are put in box or they are crossed out. So finally, we get the optimal assignment as A, that is machine A is assigned to job 1, and then machine B is assigned to job 4, machine C is assigned to job 2, and machine D is assigned to job 3. And the minimum cost of assignment is thus ₹78. Until now, we have discussed assignment problem and its mathematical formulation. We have also derived some important results based on which the Hungarian method was developed. We have also demonstrated the Hungarian method for an example. Now, we proceed to see some variation of assignment problem and also some of its applications. Let us now discuss some variations of assignment problem. First, we consider restrictions on assignment. Here we consider the problem of assigning 4 operators to 4 machines, and their assignment costs are shown in the following assignment cost matrix. Our objective is to find the optimal cost of assignment. We notice that the operator A cannot be assigned to machine 3, and also the operator C cannot be assigned to machine 4. To resolve this problem, we consider a large cost in these 2 cells and proceed as usual to find the solution of the assignment problem. For this problem, we assign a cost 10, which is greater than all the costs of the cost matrix. Then, following algorithm of Hungarian method, we subtract the smallest element of each row from all other elements of that row, and then we subtract the smallest element of each column from all other elements of that respective columns, and then we draw the least number of horizontal and vertical lines. This slide shows that the number of horizontal and vertical lines is 3. So, further improvement in the solution can be made. For this, we follow the same technique of Hungarian method, and in the next stage again we draw the least number of horizontal and vertical lines, and again we find that the total number of lines is not equal to the order of the matrix. Then we also proceed to further improvement of the solution by following the technique of Hungarian method and draw the minimum number of horizontal vertical lines in the next stage. This slide shows that we are reached at the optimal solution, as because the number of horizontal and vertical lines is equal to 4, which is equal to the order of the matrix, and then we make assignment as shown in the slide, which is the optimal one, and we get the total cost for the assignment, which is equal to 14. Now, we consider an assignment problem which is unbalanced one. To make it a balanced one, we consider fictitious rows or columns in the cost matrix, and then we follow the method which is Hungarian method to solve the problem. Similarly, for a maximization problem, we subtract all the elements of the given matrix from the highest element, and then the given maximization problem can be reduced to a minimization problem, and minimizing opportunity cost produces the same assignment solution as the original one. If the cost matrix of an assignment problem contains some negative costs, then we add to each element of the rows or columns a quantity sufficient to make all the cost elements non-negative. Now, we proceed to show some application of assignment problem. The best example is traveling salesman's problem. Let me first define what is a traveling salesman problem. Suppose that a salesman plans to visit each of n cities once and only once, and return back to the city from where he started. The distance between each pair of cities is known, and the objective is to determine the shortest route which the salesman can take. Since there are n cities, there are factorial n minus 1 possible ways for his tour. Let Cij be the distance between city I to city j, and Xij is equal to 1 if the salesman goes directly from city I to city j, where I not equal to j, and Xij equal to 0 otherwise. Since each city can be visited only once, we have sigma Xij I equal to 1 to up to n minus 1 equal to 1, where j equal to 1 to up to n and I not equal to j. Again, since the salesman has to leave each city except city n, therefore, we have sigma Xij j equal to 1 to up to n equal to 1 for I equal to 1 to up to n minus 1, where I not equal to j. Thus, the objective function is minimize z equal to summation I equal to 1 to up to n minus 1, summation j equal to 1 to up to n Cij Xij. Since Cij not equal to Cji is, this condition is not required, therefore, Cij equal to infinity for I equal to j. However, Cij is greater than equal to 0, and Cij plus Cjk should be greater than equal to Cjk. That means cost of traveling from ith city to jth city and then jth city to kth city is greater than equal to cost of traveling jth city to directly to the kth city. Now, let us consider an example and see how this traveling salesman problem can be solved by solving an assignment problem. A traveling salesman plans to visit 5 cities, city 1, city 2, 3, 4 and 5. The travel time between these cities is shown in the following table. You see that the travel time from city 1 to city 1, city 2 to city 2 and city 3 to city 3, similarly city 4 to city 4 and city 5 to city 5 is taken as infinitive, because the salesman need not to travel the same city, he has to travel from one city to another one. Now, the problem is how should he schedule his touring plan in order to minimize the total travel time if he visits each city once a week. Now, following the Hungarian method, we can easily find an assignment. The table shows that the optimal assignment forms two sub loops, city 1 to city 5 and then coming back to city 1, and then city 2 to city 3 and then city 3 to city 4 and then city 2. So, in order to make this as a solution of traveling salesman's problem, we look for the next minimum value in the table. The next minimum value is 1 in the cell 1 2 and 4 3 and 4 5. So, instead of assigning 0 in cell 1 5, let us assign to the cell 1 2 which contains 1. Then obviously the assignment in the cell 4 2 should not be there. We have to assign either in cell 4 3 or in cell 4 5. If we assign cell 4 5, then we get an optimal solution because it makes a cyclical order. The salesman will travel from city 1 to 2, then 2 to 3 and then 3 to 4, 4 to 5 and he will come back to 1. Instead of assigning in the cell 4 5, if we assign the cell 4 3, then this cyclical order will not get. That means we are not getting a feasible solution. In this model, we have so far learned how to solve an assignment problem by Hungarian method, and also we have studied some variations of assignment problem and application of assignment problem as traveling salesman's problem. With this, we conclude this module as well as our chapter 2.